Our next speaker is Heng-Yoon Zhou from Harvard. His talk title quantum computation with quantum LDPC codes in reconfigurable atom arrays.
Great. Thank you. Can you all hear me well in the back? Yeah. Okay. Great. So my name is Harry, and I'm excited to tell you about some of our recent work on quantum computation with quantum LDPC codes in reconfigurable atom arrays. So I should highlight that this is a collaboration with many great people, and particularly Qian and Pablo did a lot of the important numerics that was really crucial for this project. So as we've been hearing throughout this session, it's really a big challenge as we think about kind of going to large-scale quantum computation. In particular, if we think about the physical error rates that we have today, on the order of somewhere in between 10 to the minus 2, or if your systems are very good, 10 to the minus 3, that is still a huge gap to where we want to be with these large-scale algorithms. For example, if you think about these kind of standard compilations of, say, Shor's algorithm, you're typically looking at error rates that might be somewhere on the order of 10 to the minus 12 to 10 to the minus 15. And that's very far away from what we can have today with physical qubits, but even what we might imagine having in the future just at the physical level. Fortunately, a lot of the techniques have been developed in this field to use quantum error correction to bridge this gap. And in particular, when you're using error correction, there's this hope that you can get an exponential suppression as you increase the system in a polynomial fashion. And that's really how we can get away with still somewhat reasonable resources, yet going to these super low error rates. But at the same time, as we've also heard in the earlier talks, it is still very challenging, even with that fact, to get to the error rates that we want to have. They still demand a lot of resources. And so in today's talk, I'll tell you a little bit about some of our ideas towards kind of implementing new families of quantum codes that could bring those gaps a lot smaller, and in particular, seeing how we can implement them in a hardware and control efficient fashion. So what I'll be telling you a little bit about today is some of our implementation blueprints for memory and logical gates in these so-called quantum LDPC codes that I'll introduce in a moment, where we can hope for an order of magnitude saving in terms of the physical qubits that we require when replacing these standard surface codes with these quantum LDPC codes. I'll tell you a little bit about how the characteristics of these codes are actually very well tailored and matched towards the system characteristics of the control that we have in these neutral atom systems, such that even when we're looking at very large system sizes of maybe thousands of qubits per block, we can still actually control the qubits in a very efficient manner, such that we're looking at on the order of, like, say, 10 control lines, despite we're trying to do a very complicated kind of computation with these kind of pretty complex large block loads. So before I dive into the details of the code, I'll first tell you a little bit more about the platform that we work with. So the system that we work with are these so-called neutral atom arrays that you may have been hearing quite a bit about in the last few months. And the particular flavor that we use is what we like to call the dynamically reconfigurable architecture. So in this architecture, we have individual optical tweezers that are trapping individual atoms. These atoms have these kind of different types of states that we can use for different purposes. So we use the so-called hyperfine qubit encoded in this hyperfine 0-1 basis as a kind of our actual qubit. This has a very long coherence time, and so it kind of serves as a very good memory. We can also do very high fidelity single qubit manipulations with them. So it has kind of over a second of coherence, and if we want to drive kind of either global or local single qubit gates, we can both get relatively competitive gate fidelities. And actually, I should mention that a lot of the work was pioneered by our previous speaker, Harry Levine. We also have entangling gates through the use of this excited Rydberg state, which is strongly interacting. So this gate, you can roughly think of as kind of each qubit, when it gets excited into this Rydberg state, it becomes very big and fluffy and blocks its neighbors from getting excited. So that gives you the interaction that ultimately leads to these 2-qubit gates. There have been now multiple demonstrations of fidelities on the order of 99.5%, and people generally understand quite well where the noise sources are in these systems. So there's also quite a lot of optimism that we can really push this to something on the order of 3 nines. Finally, kind of the dynamically reconfigurability of this architecture means that we can kind of pick up some subset of atoms. I'll tell you a little bit more in detail how exactly that works later on. But we can pick up some subset of atoms, move them around, and essentially, because the gate mechanism relies on this kind of blockade, anytime 2 atoms are nearby, when we flash this global laser beam, we'll essentially be doing parallel 2-qubit gates between many of these kind of pairs of qubits. So we can get, with relative ease, kind of a very good parallelism across the whole system and execute these same gates with a similar fidelity. So using this architecture in an experiment led by Harvard, we recently showed that you can really take this and now starting to think about kind of early logical quantum processes. So in this case, the architecture kind of consists of different zones for different operations. We have a storage zone to store our qubits away when they're not doing gate operations. We can kind of pick up an entire block. This time we're kind of directly controlling an entire logical qubit consisting of dozens of physical qubits, move them either into the entangling zone to do entangling operations for syndrome extraction or for kind of logical gates, or move them to the readout zone for mid-circuit readout. Combined with the fact that we have this fault with these kind of high fidelity physical gates, we can also kind of use this aspect that we're directly controlling blocks to do high fault tolerant transversal logical entangling gates. And kind of really this architecture now enables us to have some degree of non-local connectivity where we can flexibly reconfigure where we're putting the qubits at the logical level. But also I think a very important feature is that this really has parallel efficient classical control. So we've heard a little bit about various incarnations of hardware efficiency earlier in the session. I think a very important theme that we're very excited about going forward is also to have the parallel efficient control. So really the control side is oftentimes what is challenging when you scale to many physical qubits. And I think solutions like this, where you're really going and kind of grabbing an entire grid of physical qubits that constitute a logical qubit, is a very nice way to kind of reduce those control bottlenecks. And I should also mention that tomorrow, Dolev from Harvard will give a very good talk on kind of the details of this logical quantum processor. I'll just mention kind of a few highlights of this work. So we can kind of operate this in a zone fashion where we kind of prepare some code states and then put them back into the storage. So you can see here kind of a movie rendition of what we're doing. We're essentially repeatedly taking physical qubits out, going into the entangling zone and making steam codes. 2 copies are made and then compared against in order to perform fault tolerant preparation. And so this allows us to say prepare 40 logical qubits and using them to then prepare 20 fault tolerant logical qubits of a 713 steam code or color code. Another thing that we can do is try to kind of probe how things scale as we go to larger code sizes. So this is a very important aspect of quantum error correction, where you want to see your logical performance at some level improves as we kind of increase the code distance. Making use of some new correlated decoding methods that Maddie from Harvard will also talk about tomorrow, we were able to show that we can actually kind of improve the fidelity of preparing a bell pen. In this case, we're not doing intermediate rounds of error correction, which will be a very important next step to really fully kind of extend the depth of a full quantum circuit. So with these, I've told you a little bit about where the logical quantum processors today are. We're able to prepare bigger quantum codes now with surface codes as large as distance 7. And I didn't talk about it here, but you should check out Dolev's talk tomorrow, where we also kind of started doing complex scrambling circuits with small 3D codes and hundreds of logical entangling gates. So we can kind of go along one of the 2 axes. We can either go to bigger codes or we can go to many logical qubits. But really, ultimately, as we think about these larger scale systems, we really want to do both, right? We want to kind of have both bigger codes in order to get much better error suppression, while at the same time having many logical qubits so that we can actually do the quantum computations that we're interested in. But reaching this scale is quite challenging, in particular, if we think about the typical parameters that people use to characterize a quantum code. So n is the number of physical, usually people annotate the number of data qubits. K is the number of logical qubits that you have in the system. And D is the code distance, which characterizes kind of how many errors can cause a logical error, and roughly speaking, is a pretty good proxy for error correcting power. We want to have large K and D while having as few physical qubits as possible, right? And if you look at kind of the standard surface code schemes that people look at, for example, this very nice paper from Gidney and Akera that tried to really look at all of the details of compiling the surface code, or this nice paper from Daniel Latinsky, where he studied kind of the overhead of the surface code, you really see that you're looking at millions of qubits when we try to do it in just the standard surface code scheme. And indeed, this was the motivation of a lot of the earlier work also in this session that we heard about. So we would really like to find methods that at least do better than kind of this vanilla surface code, which we know is very costly. Unfortunately, there is this so-called BPT bound, which constrains what you can do in a 2D local system. So if you have a 2D local connectivity, then actually the best parameters that you can get between these kind of number of encoded qubits, the distance, and the number of physical qubits is constrained by this KD squared is less than or equal to n. And this is actually saturated by the surface code. So you can't really do much better without going to more kind of different connectivities. But there do exist better codes if you are willing to relax that restriction. So for example, there even exist codes where both the number of encoded qubits and the distance scale linearly. This is what people call good quantum LDPC codes. But even if you don't want to go all the way there, even if you just want to get a little bit better parameters, you actually still need to have kind of a certain degree of non-locality as characterized more carefully in terms of how many long-range bonds you might need in this paper by Baspan and Krishna. So we've already seen in the earlier works, this is from an earlier paper from Harvard, that you can already do some of these non-local connectivities. So for example, in this movie here, it actually corresponds to the syndrome extraction, one syndrome extraction in the Z basis for the toric code with now kind of this actual periodic boundary conditions. So there are these non-local connectivities in neutral atoms, but does it really work well with this parallel efficient control? In particular, if you look at the movie here, these atoms are actually moving in a grid, and that's due to our control constraints. And indeed, if we think about quantum LDPC codes, if you just ask DALI or your favorite machine learn kind of a generative AI tool to produce a figure for you, it might look kind of pretty random with kind of all kinds of twists everywhere. So it might not be clear that you can actually implement this in a hardware efficient manner. In particular, the tools that we use to move these qubits around are actually so-called AODs or acousto-optic deflectors. And what these essentially do is kind of copy one beam into a row of beams. And if you have two of them, then you can kind of get a grid. So there's a very clear structure where we can easily translate or rescale, and rows and columns don't cross. But it might not necessarily be suitable for an arbitrary quantum code. Fortunately, as we've been hearing earlier today, quantum codes often have a lot more structure. A very nice structure that we'll be talking about in a moment is product code structures. But there's also complementary work that Ted showed earlier, and also there's some very nice work also that came out from Fred Chong's lab and many other places, thinking about how these structures can actually naturally be embedded. And so here what we're going to make use of is kind of some of the features of how the operations in neutral atoms for moving are actually highly structured. So I'm going to give you just a very simple model for neutral atom move operations. This is not a complete set, but it kind of suffices actually to capture most of the types of operations that we like to do. So the way you can think about it is that you have a 2D rectangular array of sites and qubits, and we can kind of pick up any rectangular subarray of qubits and move them to kind of another empty subarray and then drop them down. And then when we want to do gates, essentially, the way you can think about it is that we can kind of move certain pairs of qubits to be neighboring. And then once they're neighboring, we can just flash a laser beam and we'll do parallel 2-qubit CZ gates between every pair. So with this model, you see that there's a very clear kind of structure in the native control efficient operations supported. And in particular, this kind of product is a very common structure. And the natural question then is, how do these natural structures relate to the structures that you have in quantum LDPC codes? So these quantum LDPC codes, I guess I should actually also, just as a reminder, the LDPC stands for low density parity check. So it means that every data qubit or check qubit is only talking to a constant number of other physical qubits. So that kind of constrains effectively the degree of the system. And a typical way that people like to construct these LDPC codes is through this so-called product construction. So if you look at kind of any quantum LDPC code review or 101 lecture, the first thing that people like to introduce are these so-called hypergraph product codes that are constructed by taking a quantum code constructed from a so-called product between the two classical codes. So more specifically, the surface code that we've been hearing about is actually the classical, the hypergraph product code of two classical repetition codes. So here what I'm showing is a classical repetition code where these squares are the checks and these bits are the circles are the classical bits. And so we're essentially kind of checking the parity between the neighboring bits, and that's kind of our classical repetition code. And if we have two of these repetition codes, we can take the following product, where for every intersection of a bit and a bit, we'll put a qubit. And every intersection of a check and a check, we'll also put a qubit. And then every intersection of a bit and a check, we'll put a Z stabilizer. And for the other one, we'll put an X stabilizer. Okay? So we kind of have these two lines that then when we take this product, we get a square. And if you look closely, actually, this is essentially the unrotated surface code. So you have kind of these data qubits that are placed at these locations. And then we have these checks that in the bulk are checking essentially X or Z's of its four neighbors. Okay, so the surface code is actually a special case of this hypergraph product code. And actually, if we take a more general code, and I should also mention that maybe another feature is that the connectivity that you have here on the quantum code side is actually inherited from the classical code. So for example, if you have a bond between a bit and a check here, this will kind of translate to a set of bonds in the same direction. So now we can put in a more general classical code. And actually, it turns out that if you just kind of take a random construction for classical codes, you can actually pretty easily get parameters where the number of classical encoded bits scales and the distance scales linearly with the number of classical data bits that you have. And so if we take the same construction and kind of apply the same rules where you kind of copy the bonds from the classical code to the quantum code, we'll actually obtain a quantum code that has parameters now where the number of encoded logical qubits scales linearly with the number of physical qubits, while the distance scales as a square root. So we kind of get the same distance scaling as a surface code, but now we have the extra advantage of encoding many more qubits. And some of these particular constructions are also known as the quantum expander code. I should also mention that many of the subsequent code constructions that you may have heard about, including what led up to these so-called good quantum codes, they were all various flavors of generalizations of this hypergraph product. So really kind of it's like a seed that then you can generalize with successively more complexity to better code families. So how does this match the structure of what we have? Well, you can probably already guess that essentially what we'll be using is the fact that this product structure matches well with the product structure of our optical tools. So in particular, what we can do is we first do a row permutation. We saw that the bonds are all inherited in the same way across the system. So we can kind of do all of these gates in parallel simply by doing a row permutation. We can then follow it up with a column permutation, and then again in parallel execute many of these entangling gates that we want. And this gives us kind of a very nice way to implement the syndrome extraction of this hypergraph product code. Now, we still need to be able to do kind of all of the 1D permutations. That one we kind of can't get away with. But fortunately, there's a relatively simple divide and conquer algorithm that enables a log depth implementation of an arbitrary 1D permutation. So what we're going to do here is we first figure out which qubits need to end at the right in the end. And we're going to just move them all the way out to the right. Then we kind of compact the workspace a little bit down here. And then now we have kind of these two subsystems that we can then repeat the same procedure in kind of a recursive fashion. So you can easily convince yourself that this gives you a log depth algorithm. And indeed, we can kind of, again, make nice movies in software of what this might look like. So here we're kind of first doing this log depth rearrangement with successive layers. And then we do a flash of a kind of an entangling gate across the whole system. And then we can kind of repeat. One very nice thing for these kind of hypergraph product codes is that actually, even with this scheme where we're just using a single ancilla to do all of the syndrome extraction, this is actually still fault tolerant. OK, now we're doing the vertical one again. Because it's fault tolerant, it actually is very nice because you can expect to kind of have a code distance that mostly reproduces your kind of design code distance at the circuit level. So we went ahead and did circuit level evaluation. In this particular case, we're using constructions using classical LDPC codes from random biregular graphs where some nodes have weight 3 and some nodes have weight 4. And with this, you can actually construct pretty good codes. We did some screening to essentially screen for heuristics that would perform the best. And then we performed decoding with techniques that are quite similar to what Ted mentioned earlier, except in this case, we're kind of really doing a pretty deep circuit. So we opted to instead break it up into pieces for the decoding, where we're running kind of smaller rounds of belief propagation. And then at the end, running this BP plus OSD decoder that Ted mentioned. And in this case, this allows us to essentially perform circuit level decoding for kind of things like 40 rounds of syndrome extraction and kind of thousands of physical qubits. And I should also mention that there's some nice work from Shruti Puri's group. Shulin Huang and Shruti had a paper where kind of you can also further enhance these by doing some type of windowed decoding to further improve the performance. OK, so let's look at our numerical results. As we increase the code instances of this family all the way up to a 10,000 qubit family, we see that kind of the performance very clearly shows this type of threshold-like behavior. This logical failure rate is the chance of kind of per round any qubit among the logical qubits failing. And if we look at the error threshold under a circuit level depolarizing noise, for now without adding idling errors, then we extract a threshold that is close to 0.6%. And because the neutral atoms have relatively long coherence times, adding in realistic idling errors actually only slightly shifts the thresholds in these regimes that we're looking at. And in the future, if one kind of wants to go to even larger sizes, you could also consider, for example, having a concatenation at the lowest level. So this is pretty promising, not quite as high as the surface code threshold, but still fairly competitive. We can kind of go ahead and look at, if we put in a 0.1% error rate, what the resource overheads for kind of different sizes really are. So in particular, if we look at the parameter space and comparing the resource costs of the surface codes against these different families of quantum LDPC codes, in this case, actually, we kind of numerically did both the hypergraph product code and the lifted product code, which is kind of a slightly more advanced version of these products. You see that even at the size of 1,000 or so physical qubits, you can already start outperforming the surface code by quite a bit. And really, in these scales that we're looking at for kind of large-scale quantum computation, you're really looking at over an order of magnitude in terms of the resource saving. So this so far is numerics on kind of just doing a memory experiment. But what we really want to do is actually do computation, right? We're interested not just in storing the information, but also in manipulating it. And this is actually quite non-trivial for these types of codes, because if you look at it, kind of all of the logical qubits are mixed up in this big block. And so you need to have access to really kind of take out some individual logical qubits and operate on them individually. So there's been a couple of different works in the literature. There are these fault transversal gates that Ted also mentioned. There are these lattice surgery schemes which essentially kind of build on the side and do some extra operations. And the scheme that we opted to go for is a very similar scheme to this lattice surgery scheme, except we slightly adapted it to take a little bit less spatial footprint through some optimizations. So how does lattice surgery work? For those of you who haven't been kind of thinking about error correction quite every day, essentially the idea, in this case, just illustrating it with a surface code, is that if you have two logical operators, if you join these two code patches together in this fashion, then what we get is that the new stabilizers here, these kind of two stabilizers that I'm showing here, these actually exactly correspond to the product of the two logical operators that you originally had. And so if we just kind of merge two code batches like this, then actually if we look at the boundary, we can use this information to kind of extract what the product of those two logical operators are. And so if we do d rounds of kind of repetition, then this actually allows one to fault tolerantly measure the value of z1 times z2 of these two logical operators. And this same idea actually also readily generalizes to the LDPC code case. So here what we're essentially doing is kind of constructing an ancilla patch where one boundary looks the same as the surface code and one boundary looks the same as the LDPC code that we're looking at. And essentially, it's kind of the same hypergraph product procedure that I told you about earlier, in which this is essentially just kind of a hypergraph product of two subcodes. This one is a repetition code. This one is kind of a subcode of a column of the original code that you have. So using this technique allows us to perform logical gates. And we actually also went ahead and performed circuit level simulations of this. And at first sight, actually, it might not be obvious how well this will fare in the circuit level case, because these two codes look pretty different. Some of the decoders that people have for LDPC codes heavily rely on certain properties called expansion, which is something that you don't necessarily have in the surface code. But nonetheless, actually, these kind of BPOSD type decoders actually are quite generic and still give you a threshold. So the circuit level simulations that we showed have kind of thresholds that are kind of on the same order of the thresholds that we see for the memory, which is encouraging, although further numerics and kind of further improvements on the decoders are definitely needed. So in conclusion, I've told you a little bit about some of our recent ideas of hardware, of kind of how you can implement these traditionally regarded as more exotic quantum codes with the capabilities that we actually have in hardware today. And I think a very important feature is that also the implementation of these is in a fashion that is actually quite hardware efficient and more particularly control efficient, where all of the things that I showed you are actually things that one can really think about implementing with essentially one pair of AODs with very nice parallelism of your control. So you're essentially looking at kind of 10 or so control lines maybe when you're implementing 1,000 qubit kind of logical operations. And so this, I think, really hopefully inspires you to also think about these types of approaches in other systems. And I think as we look forward, I think there'll be a very nice synergy of the design between thinking about the algorithms, thinking about the error correcting codes, and also thinking about kind of the native hardware capabilities. We heard earlier in the talks today in terms of kind of various other incarnations of hardware efficient design in the earlier talks. And I think there's also plenty of room to also think about how this interfaces with other aspects that we would like to think about in terms of algorithms and other aspects of error correcting codes. So with that, I'd like to thank my collaborators, particularly Tian and Pablo, who are really driving a lot of this work forward. And thank you for your attention.
Thank you for a very nice talk. If you have any questions, if you could come down to the microphone, or you could.
I have a quick question. So it's kind of like a slightly technical question. So for this readable circuit, how many layers can you possibly do, and also compare with like I don't do the tweezer transportation, and after I do the transportation, what's the difference between the layer? Like if here without doing transportation, I can do 10 circuit layer depths, and how many circuit depths can I do? Like if I need to do it every other time.
Yeah, that's a great question. So I guess in these demonstrations that I showed at the beginning, with these logical algorithms, the depth was maybe 7 or 8 circuit layers.
Okay.
That was what we showed. Eventually, you might worry about heating, which eventually will cut into your gate fidelity or cause loss. We didn't quite see it at the scale that we were operating at, but that is something that would be important to address in the future as well, as we look at these like very deep kind of quantum circuits.
I see.
Yeah.
Since you are teleporting from the hypergraph product code to the surface code, are you assuming to maintain this advantage that the amount of qubits you're computing on the rate goes to 0 as the number of physical qubits increases?
That's a great question. Yeah. So in this particular case, we are kind of limiting the parallelism of application. Essentially, if you had like k qubits, then roughly speaking, we kind of only operate on square root k of them at a time. And so this will be a little bit algorithm dependent in terms of whether this will give you an additional time overhead or not. There is actually a nice analysis from Fred Chong's group, which essentially looks at like concrete algorithms and does this loading in and out. And what they find is that you can at least still have some advantages with this in terms of the space-time footprint. The advantage is, of course, a little bit diminished. And so I think a very interesting research question is to also think about how maybe you can directly do the gates without ever using any kind of surface code or like surface code flavored thing.
Thank you.
Well, there's another question.
Have you tried implementing a code that can do, for example, a non-tempered gate conversely or something like that?
Yeah, that's a great question. Oh, yeah, that's a great question. So the question was, have we considered implementing a code that has non-Clifford gates? So actually, in these kind of recent results from Harvard with the logical algorithms that I encourage you to check out Dolev's talk tomorrow on, those actually do contain essentially small 3D codes that do have kind of transversal non-Clifford gates. For the LDPC codes, there aren't very good constructions that people have, but there have been constructions with hyperbolic codes. There's a nice paper from IBM by Guanyu Zhu et al., where they show that you can have non-Clifford CCZ gates essentially operating in parallel across kind of many different blocks within the LDPC code. So that's something that I think the constructions aren't quite there yet, but they could become interesting as people continue to develop these.